Right, when last we left, we were starting to talk about lattice energy, and I'm going to show what's the process of calculating lattice energy, and it's done through a process called the Born-Haber cycle. Okay, so, and in the Born-Haber cycle basically utilizes Hess's law, okay, in that we can add up the enthalpies of individual steps in order to calculate the enthalpy of an overall process. So we're not going to expect you to do any of this, okay, but I want to show it so that you can get an idea of where lattice energy fits into the forming of an ionic substance. Okay, so our first step in the process is sublimation. Okay, I need all of my ions, or excuse me, all of my compounds to be in the gas state. The next step is atomization. So I need to make everything into a single atom. Okay, so if I have, for example, like Cl2 or H2 or something, I need to break that apart so I have a single atom of that component. Next is ion conversion. Okay, I need to make everything ions. So I'm going to remove an electron from the cation. I'm going to add an electron to the anion. Okay, and there's energy associated with those. And then finally, we have making of our solid. Okay, and that is actually where the lattice energy comes into play. Once I have gaseous ions, they can come together to form an ionic solid. Okay, so let's take a look at what that process looks like. So we begin over here on the left where it says start. Okay, and what I have is some solid sodium and some chlorine gas. Okay, neutral components. And we know what the enthalpy of formation is for that compound, right? So it's a release of 411 kilojoules, right? So we're not starting at zero. We're starting a little bit above zero energy, okay? So our first step is to sublimate, and there's an enthalpy associated with that. We have to put 107 kilojoules of energy into our components in order to sublimate my solid sodium to gaseous sodium. Then I need to break apart my Cl2 into a single Cl. Okay, so atomizing the chlorine gas requires another energy input of 122 kilojoules. And then I'm going to ionize my sodium to sodium plus. I'm going to pull off an electron. There's an associated energy input for that of 496 kilojoules. Okay, so far we're climbing up and up and up in our energy requirement. Okay, this is all energy that has to be put into the process. And whenever we have to put energy in, that is energetically unfavorable. Okay, the universe would rather get energy out rather than putting energy in. Right, so now I have sodium ion in the gas form and chlorine neutral in the gas form. So putting an electron onto the chlorine is an energy release of negative 349 kilojoules. So now that I have sodium plus gas and chlorine minus gas, I can form my solid. Okay, and that energy release going all the way back down to the bottom of our formation, that is the lattice energy. So it's a very large energy release. Okay, and that energy release is what makes this an actually energetically favorable process. Okay, so if we ended up having to put energy in, the net result being a positive energy, this solid would not form on its own in nature. Okay, so this is what the lattice energy does for us. It takes all of these energy inputs, and then it makes the process as a whole energetically favorable. Right, so, like I said, you won't have to calculate those values. I have taught other classes where you do, but in this textbook, we do not expect you to calculate lattice energy, but you do need to be able to predict qualitatively based on periodic trends. Okay, so lattice energy is basically electrostatic. Okay, and because it's electrostatic, I can use Coulomb's law to talk about it. Okay, and with Coulomb's law, we have the electrostatic energy is related to the charge of the components, so the charge of component A times the charge of component B divided by the distance between them. Distance. Okay, so if lattice energy is basically electrostatic energy, we can say the energy of the lattice energy is proportional to Coulomb's law. So in more specific terms, we'll be talking about the cation charge times the anion charge divided by the distance from their atomic radii. So the cation radius plus the anion radius. Okay, so thinking about how fractions work, as your denominator gets larger, your value gets smaller. So in this case, as my radius goes up, my lattice energy goes down. So bigger atoms will have consequently lower lattice energy. So when radius goes up, lattice goes down. Right, now if radius is basically constant, if my charge goes up, my lattice goes up because the charges of the ions are in the numerator. So a bigger numerator results in a bigger value. So when charge increases, so does lattice. Right, so let's compare a couple of different compounds and see qualitatively whether we can determine which one would have a greater or lesser lattice energy. So let's compare rubidium iodide and lithium fluoride. Okay, so all of these components have charges of +1 or -1. Okay, so there's no difference in charges between a rubidium and a lithium or an iodine and a fluorine. They all have +1 or -1. So the difference is size. Okay, so rubidium and iodine are much lower on the table, which means that they are larger ions. Right, so as size goes up, lattice goes down. Right, so rubidium iodide will have a lower lattice energy. Right, so let's compare a couple of different species. Let's compare this time potassium chloride and calcium sulfide. All right, so potassium and calcium are about the same size. They're right next to each other on the table. chlorine and sulfur are also right next to each other on the table, so they're about the same size. All right, so let's look at charge. So potassium and chlorine are +1 and -1. Calcium and sulfur, on the other hand, are +2 and -2. Right? So as charge goes up, lattice goes up. So calcium sulfide will have greater lattice energy. Okay, I'm going to go ahead and pause this video right here, and we'll pick it up on the next video where we start to talk about bond enthalpies.